Welcome to extra video clip E1, in which we discuss concurrency. When we want to discuss concurrency, we first have to look at sequential executions. A set of process activities are sequential if the process model prescribes that they are always executed in a sequential order, so one process activity after the other. So at each point in time, at most one process activity is running. Here we just use a sequence flow to define sequential execution of activities A, B, and C. And as we discussed earlier, this execution of A, B, C is conducted sequentially. First A is executed. When A finishes, only then B can start. When B finishes, only C can start. Still, we can further illustrate sequential executions using time diagrams. And I like to introduce now the concept of a time diagram by the following sketch. So in time diagrams, time proceeds from left to right. So time t proceeds from left to right. And on this time axis, we can capture the duration of the activities A, B, and C. So at some point in time, activity A starts. When A is finished, B can start. That does not mean that immediately after A, B starts, but it can stay for a while in the enabled state before some person decides to now execute activity B. So assume here B starts, here B terminates, and afterwards C is executed, which might take a bit longer. And we can even say, well, the running phase of A started maybe at 8 o'clock sharp. A terminated maybe at 8:20 in the morning. So B started a bit later at 8:40. B terminated maybe at 9 o'clock. C started at 9:10. And C terminated maybe at 9:30. So that gives you an idea of the execution ordering of A, B, and C, and also we added time here. But it's important to see here that the time in which the activities are executed are, let's say, stressed here. So there is first a time in which A is executed, then a time in which B is executed, and then a time in which C is executed. And of course, A, B, and C are sequential. All right, when we analyze processes, we look at traces. We investigated this in week 3 of our course. And there we abstract from the concrete running phase. We do not look at the running phase, but we just look at the traces. And to be able to look at the traces, we have to abstract from the concrete running phase. So we now discuss how we come from the time diagram to the traces. Again, we have the sequential ordering, A, B, and C. And so we first have the A, then we have the B, and then we have activity C. We can now somehow shrink the running time to 0 to just abstract from the state running of the activity instance and just look at the activity itself. So in that case, it's very simple. The trace would look like first A, then B, then C. And that's the only trace that is produced by this process model. Often we look at the termination time, so the time when A terminates. That's the point where the activity A is conducted, and then we would write an A, B, and C the same. Okay, but we can have sequential executions not only if we have sequences that we look at, but also when we have XOR splits in our process model. Even if when we just have XOR splits, we also end up with a sequential execution. In order to investigate this in a bit more detail, there is the following diagram that we see here. And now let's look at the time diagrams we have. Well, there are three options of executing this process, obviously. Either the upper branch is taken, the middle branch is taken, or the lower branch is taken. So therefore we have three time diagrams. The first one is first A, then B, and then the final activity E. Now this is the case when the upper branch is taken, where B is executed. And the other time diagrams would look like this. So again, there is an A, but then there can be a C, which can also be a bit longer, of course. And afterwards we have the E. And another diagram, time diagram is first the A, and then we have the D. In this case, the lower branch is taken. And finally, we have the E again. Okay, this is the time diagram view, and now, of course, we can do the same. We abstract from the runtime state, or from the running state of the activity instance, and just look at the termination. And there we have traces A, B, E that would reflect the first time diagram. First A, then B, then E. But we could also execute A, C, E. First A, then C, then E. And finally, ADE is also a valid trace for this process model. In any case, it's still sequential, so all activities are executed sequentially, and at each point in time, there is at most one activity running. So often we have just one activity running, but in the gaps between there are no activities running. Therefore, we say up to one activity can be running in case of sequential executions. So let's now look at concurrent executions. A set of process activities are concurrent if the process model prescribes that they can be executed independently from each other with an arbitrary interleaving. Of course, also arbitrary ordering. At each point in time, multiple concurrent activities might be running. We have concurrency in our process model when, for example, we have an AND split and an AND join. AND splits. So these three activities are concurrent because they can be executed in any ordering with any interleaving or concurrently at the same time as we like. To stress this in a bit more detail, we also look at time diagrams in this context, and we see that time diagrams for concurrent processes or concurrent activities look a bit different from the ones we've seen before. So what is the difference in detail? All right, so the time diagram, each time diagram starts with executing activity A, since this is the first activity that is executed for this process model. That's activity A. All right. So after activity A is executed, what can happen? B, C, and D, all three are executed for each process instance. Yeah, so an AND split, when we have an AND split, all outgoing sequence flows are signaled. So in any case, B, C, and D can be executed. So for instance, B is executed immediately. Then also almost at the same time, maybe a bit later, C is executed. It's very fast. And then maybe the execution of D starts here, takes a bit longer. So what we see here is that B, C, and D are concurrent. They are independently. They are executed at the same time. Almost at the same time. C is a bit shorter, starts a bit later, so there is an arbitrary interleaving. This is what we meant by arbitrary interleaving. Of course, C can also be executed a bit before B or a bit after B, or in any interleaving with B and also with D. However, E can only be executed when all of these, B, C, and D, have completed, have terminated. This is the semantics of the AND join on the right-hand side here. So after all these activities have been completed, we have the E. And that is one sample time diagram. When we look now at the traces, we also have to shrink the interval in which the activities are executed together. So we can look at the termination to do that. And what do we see? Well, the first thing, let's first look at the ordering of the termination of the activities here. And that would give us the first trace, and that is A, the first activity that terminates. Then we have C. Then we have B. Then we have D. And then we have E. That's the first trace. That's one trace that is possible here. A, C, B, D, E. That's the order of termination. But there are quite some more. So we can, let's see if we can put them all together here. Maybe I write it, the traces here on the right-hand side. We have A, then B might be the next one. Then we have C, D, and E. But we can also have AB, and then AB, and then DC. That's also a valid trace here. Okay, we can have AC, first A, then C, and then we have BD. We had this already. But we can also have DB, and then we have AD, and AD, we can have a BC. But we also can have AD, C, oh, sorry. We have, here we go, AD, C, C, pen, B, and then the E. So we have, overall, we have these 6 traces that are created, that are allowed by this process model. All right, but in the example and also in the homework, we investigated the OR split. And the OR split allows any number of branches, outgoing branches, to be signaled. So that means that we have to, in order to investigate what the OR split does, we have to investigate all possible executions. Since we don't have too much space to discuss a time diagram and all the traces, I like to assume that here the first branch is taken, the second branch is taken, but that branch is not taken. So that's a particular assumption here, but we can easily extend it also to a case where another subset of the branches is signaled. All right, let's now look at the time diagram. And so the first 2 branches are executed concurrently. However, we have, of course, to make sure that B can only start after A has finished. Of course, we have to make sure that this is true. So we can have a sample time diagram here that maybe starts with the A. And then maybe B is not immediately starting, but there can be the C. C can be executed. And only then the A can start, the B can start. Yeah, that would be a valid trace. So one trace would be A, C, B. Yeah, first A, then C, then B. Actually, we would come to the same trace if there was an overlap. If we have something like this, we have the A here, and then we have maybe the C here, and then here we have the B. Also in that case, when there is a real overlap in time between activities AC and BC, we would come to the same trace since we look at the termination operations. Also that would end up the trace that we have here. First finishes the A, then the C, and then the B. All right. That summarizes the extra video clip E.1, in which we discussed concurrent execution or concurrency in process models. We first look at sequential executions, in which at each point in time, at most one activity is executing. We've seen that if we only use sequence flow in process models, we end up with sequential executions. But we also end up with sequential executions when we have XOR splits only. We looked at time diagrams to illustrate the temporal aspects of activity executions in process models. And we abstracted them to traces, where we abstract from the running state and just give the name of the activity when it terminates. And traces are very useful when we analyze business processes. We looked at concurrent execution or concurrency in process models, and we found out that whenever we have an AND split, we find concurrency because all branches are signaled. So a number of activities can be executed in any order or with any interleaving. And we also find the same in the inclusive OR split, where any number of outgoing edges of an XOR split can be signaled so that the respective branches are then executed concurrently.